All right, in this video we're going to be talking about improper integrals, and improper integrals are going to be talking about integrals that go to positive infinity or negative infinity, or there might be a vertical asymptote somewhere along the interval where your function approaches positive infinity, negative infinity from the left or right. So that's just talking about this right here. One type of improper integral is a definite integral, meaning we do have boundaries, where either the upper limit or the lower limit is infinite. We write these integrals with an infinite bound using this notation. So if you have an integral that goes from a, which is some constant value, up to infinity of f of x dx, we can write that, or we need to write that, as a limit. And so this is going to be the limit as b approaches infinity of this integral. Because as you know, if I find the antiderivative of f of x, and then you plug in the upper value minus the lower value, you can't actually evaluate a function when you plug infinity into a variable, because infinity is not an actual value. So you have to treat it as a limit as a letter approaches infinity. And you can do the same thing as a approaches negative infinity as well. An improper integral converges or is convergent to a number, meaning you will have a solution if the limit shown above is finite. So if you work out this limit and it comes out to be a finite number, then that means that this improper integral is going to be called convergent. Otherwise, if the limit is infinite, the improper integral diverges. So it is critical that you start to learn these two terms, especially as we move into our unit on series later this semester. So converges and diverges. When your function converges, you're going to end up with a solution. When it diverges, that means our integral is going to be infinite. There is not a single number or a value that your integral is going to converge to. An improper integral cannot be convergent unless the limit as x approaches infinity of our function is equal to 0. So that's the first thing that you want to look at, is your function has to be approaching 0, which means you need to have an in-behavior asymptote of 0 for your function in order to converge. Okay? And we'll talk about that a little bit more as we move through some of these problems. All right, so let's look at our first problem here. This says the graph of f of x equals x squared times e to the negative x, and determine whether or not the improper integral could converge. All right, so here's a graph of that function, and the integral, as we know, is the area between the curve and the x-axis. So this area right here is what we're referring to. And we want to know, is this or could this converge? Well, if you go back to your definition, is first thing that we need to understand is, does the limit of the function approach 0? So you can see that our function is approaching 0 as you go to infinity. So could it converge? Yes, it could, because of that definition right there. This does approach 0 as the function goes to infinity. However, what we want to know is, does this area approach a single value, or will this area continue to grow as you move to infinity? That's what we want to look at. So the first thing that we're going to do is evaluate this integral that goes from 0 to b, understanding that b is our infinity. So if we're to evaluate this integral, the first thing we would need to do is find the antiderivative. And the antiderivative on this, we can use the tabular method for finding this, where we have u and dv, where u is going to be x squared and dv is going to be e to the negative x. And we can take our derivatives of u, giving you 2x, 2, and 0. The antiderivatives of e to the negative x are negative e to the negative x, e to the negative x, and negative e to the negative x. All right, so now we can put these together. The first is going to be positive, the next one is minus, and the next one is positive. All right, so that's going to give us negative x squared e to the negative x minus 2x e to the negative x, minus, because it's a negative e, so 2e to the negative x. This is a definite integral, so we're going to evaluate this between 0 and b. So that's going to give us negative b squared e to the negative b minus 2b e to the negative b minus 2e to the negative b minus, and then your first term will be 0, minus 0, minus 2e to the negative 0, which is 2. All right, so then cleaning that up, you'd end up with negative b squared over e to the b power minus 2b over e to the b power minus 2 over e to the b power plus 2. All right, so now what we know is we cannot actually plug infinity in and get a numerical value out of this. So what we want to do is treat this as a limit. So we are going to rewrite this then as the limit as b approaches infinity of this right here. And let me bring that over here. So now, if you think about very large numbers going in for b, well, an exponential problem is going to grow at a much faster rate than just b squared, which means your denominator is growing at a much faster rate than your numerator, so therefore this is going to approach 0. These fractions will get smaller and smaller and smaller the larger b gets. So this will approach 0. This will approach 0 as well for the same reason. Your denominator is going to grow at a much faster rate than your numerator, which means these fractions will continue to get smaller and smaller and smaller as b gets larger. Same thing will happen here. This will approach 0. Now there is no variable on this, which means this is constant. So what happens then is this approaches 0, that approaches 0, this approaches 0, and that is 2. Therefore, this area underneath the curve is going to approach an area of 2. All All right, so let's take a look at our next problem, which says that we need to graph f of x equals x plus 1 over 2x. So this is our graph of x plus 1 over 2x, and determine whether or not the improper integral, could converge. Show mathematically why your answer is correct. So the very first thing that we need to look at is, does our function approach 0? And the answer to that is no. This function, you can see from the graph, does not look like it approaches 0. Now, how do we determine whether it does or not mathematically? We treat this as a limit as x approaches infinity of x plus 1 over 2x, which is equal to the limit as x approaches infinity of 1 over 2. You can think of spit in the ocean if you remember that from back in the fall, or you can also approach this using L'Hopital's rule, because you're going to have infinity over infinity, which when you do the derivative of the numerator, you get 1, and the derivative of the denominator, you're going to get a 2, and so this answer comes out to 1/2 in either case. All right, so since our function does not have a horizontal asymptote at 0, or end behavior asymptote at 0, because it is 1/2, what that means is that this area is going to continue to add up as you move further towards infinity. You're just going to keep adding a half and a half and a half and a half and a half, and you will not be approaching a single numerical value. All right, so let's take a look at our next one here. If you think about, does this limit as x approaches infinity, which is equal to the limit as x approaches infinity of 1 over e to the x power. And we can see that as x gets bigger and bigger and bigger, your denominator gets bigger, which means this value of the fraction gets smaller and smaller and smaller, which goes toward 0. So this function does have a horizontal asymptote at 0. Therefore, we can, or this could possibly converge. Just because your function approaches 0 does not necessarily mean that your function will converge. It means that it could converge. All right, so the first thing we want to do is we want to rewrite this problem as a limit problem. So this will be the limit, and I'm just going to use a for our constant. Limit as a approaches infinity from 0 to a of e to the negative x dx. All right, saving a little bit of time, we know we would be using u substitution in here, where your exponent is u, and the derivative of that is -1, so you put a negative here and a negative out front. So your antiderivative ends up being negative e to the negative x. And this will be the limit as a approaches infinity of this antiderivative evaluated at 0 and a. All right, so this will be the limit as a approaches infinity, and what we need to do now is evaluate this antiderivative at a minus 0, and then we will come back and evaluate the limit as a approaches infinity. All right, so substituting in a, you're going to get negative e raised to the negative a power minus negative e raised to the 0 power. All right, so this becomes limit as a approaches infinity, and we'll just clean this up a little bit. This will end up being negative 1 over e to the a plus e to the 0, which is 1. All right, and we know that as a gets larger, our denominator gets larger, which means this is going to approach 0. And that's going to leave us with a value of 1. All right, so therefore, that is what this integral is going to approach, a value of 1. That's what the area between the curve and the x-axis is going to be approaching. This is a graph and some examples here for that particular function that we just did, where we have the function being f of x equals e to the negative x. This is our graph for that. We can see the horizontal asymptote at 0. And then I went ahead and evaluated some of these integrals. Remember, we're doing an integral from 0 to infinity. Well, I just plugged in some numbers so that we can actually evaluate some of these, showing an increasing value for the upper limit. So the integral from 0 to 10 comes out to 0.99995. Well, if we do the integral from 0 to 100, so I increased the upper limit of integration, came out to 1. It's actually not equal to 1. It is still a very large decimal, but the Desmos calculator is going to round that number to 1 because it was so close to 1. And you can see if you keep increasing that upper limit tenfold to 1,000, our answer did not change. The integral did not change. It was still 1. So you can see that as we continue to increase that upper limit and we go toward infinity, we're not really adding any significant area to this. It is approaching a value of 1. So that is what this area here, and the majority of it is between 0 and 5. By far the vast majority of it is between 0 and 5. That area comes out to 1. All right, so let's look at our next function. On this particular problem, we're going to write this first as a limit as a, and it doesn't matter whether you use a or b or t or whatever you want to call infinity. We're just going to say the limit as a approaches infinity of the integral from 1 to a, and I will rewrite this as x to the negative 2 dx so that we can do the antiderivative of that. We're going to get limit as a approaches infinity of negative 1 over x is what that comes out to for the antiderivative, evaluated between 1 and a. All right, so this comes out to limit as a approaches infinity. Plug in, evaluate our definite integral, so you're going to have negative 1 over a minus negative 1 over 1. And simplifying this just a little bit will give us negative 1 over a plus 1. And we can see that as a approaches infinity, this fraction will go to 0, leaving us with an area of 1. Now, just because the last problem and this problem came out to an area of 1 does not mean that they all approach 1. That just happened to be a coincidence. So let's take a look at the graph, kind of like what we did on the previous problem. This is the graph of 1 over x squared. We do have a vertical asymptote at x equals 0. So what we are looking at, though, is the integral from 1 to infinity. So we really are looking at the area from 1 to infinity as that continues on out. And so this area, well, first thing you can see that yes, our function does approach 0. We didn't really address that, but our function does approach 0 for an in-behavior asymptote. And this area is approaching an area of 1. And we did an integral over here from 1 to 10, came out to 0.9, increased the upper limit, came out to 0.99, increased the upper limit again, 0.999. So you can see that as we're increasing that upper value, we're getting closer and closer to a value of 1. All right, so what I want you to do is take a look at this problem. The only difference here is that we are going from negative infinity to positive infinity. So we are going to have to rewrite this as two limit problems. So the first one is going to be the limit as a approaches negative infinity, going from a to some constant, and it doesn't really matter what we call that. I'll just use 0 of 1 over x squared plus 1. And like I said, it doesn't matter what constant you plug in here. You can put a 1, put a 2, put a 3, doesn't really make any difference. Any constant that's on this interval, which is every constant, can be used. And so now we add the limit, and I'm going to use b approaches positive infinity from that same constant of 0 going to b of 1 over x squared plus 1. All right, so now we need to find the antiderivatives and evaluate them. So that's going to give us the limit as a approaches negative infinity. Now the integral of 1 over x squared plus 1 is the same thing as 1 over 1 plus x squared, which is tangent inverse of x, evaluated between a and 0, plus the limit as b approaches infinity of tangent inverse x between 0 and b. All right, so now we're going to substitute in. So you're going to have tangent inverse of 0 minus tangent inverse of a plus the limit as b approaches infinity of tangent inverse of b minus tangent inverse of 0. All right, so let's think about what the graph of tangent inverse looks like, first of all, for evaluating these. All right, so tangent inverse looks like this, where you do have an asymptote right here at pi over 2, and you have another horizontal asymptote at negative pi over 2. All right, so the tangent inverse of 0 is 0, and the tangent inverse of a as a approaches negative infinity. So let's think. According to this graph here, as x goes towards negative infinity, that means our graph is going to approach negative pi over 2. All right, so what this comes out to then is going to be 0 minus negative pi over 2. And that's what we get when we evaluate this limit as a approaches infinity. All right, so now we do the same thing over here. We're going to have plus, and then the limit as b approaches positive infinity. Well, tangent inverse of very large numbers. So as we move further to the right, these values get closer and closer to pi over 2. And so that becomes pi over 2. And then tangent inverse of 0 is 0. Now, you're probably wondering, well, what if I had chosen to do a different number besides 0? What if we use 2 right here, or 5? It doesn't really matter, because what we would have ended up here if we use 5 would be tangent inverse of 5 right here, and then you would have minus tangent inverse of 5. So this value and this value will always cancel out when we're adding these two integrals together, and so it doesn't really matter what constant that you're going to put in there. All right, so now this comes out to pi over 2 plus pi over 2, which is equal to pi. That's what this area will converge to. All right, so what I want you to do now is take a second and think about what we have talked about throughout this video. I want you to press pause and work this problem out on your own, and then unpause the video and reveal the answer and check your work on that. So at this moment, go ahead and press pause on the video. All right, welcome back. So take a look at the work that we've done here. The first thing is, yes, this does approach 0. The function does approach 0, so you have an end behavior asymptote there. First thing we do is rewrite this as a limit problem. So limit as a approaches infinity of the integral from 1 to a. And then we found the antiderivative, x to the negative 2 over negative 2 from 1 to a. And then just simplified that fraction a little bit. And now we evaluate, plugging a in, minus, and then plugging 1 in will give us this. And now you can evaluate this problem. So as a approaches infinity, this fraction is going to approach 0, which is going to leave us with minus negative 1/2 or positive 1/2 as our answer. So if you look at the graph of this, the area between the curve and the x-axis from 1 to infinity will approach a value of 1/2. Is it exactly 1/2? Not exactly, because it approaches. It is a limit problem. All right, you may want to go ahead and watch part 2 of improper integrals so that we can see the next type of improper integral that you will be coming across.